Let me welcome you to the 57th lecture of uh, online NPTEL certified course Drilling and Blasting Technology. In this lecture, we will learn how to carry out numerical analysis of blasting problems. In this lecture, along with me, Dr. Satyabrata Behera is there. He is already introduced in the uh, introductory slide, introductory video of this course. So, this part is mainly delivered by him, but before that let me introduce you to this subject. That numerical analysis is very special one, which has to be carried out almost many places to understand the simulation process. Uh, you know that in rock mechanics many cases before designing and actually implementing that in a practical case, we generally go for numerically simulating that one to see whether it is stable in that particular position or not. Suppose there is a building has to be created in a windy area or so, we design the building, place that in the software, then provide the wind etc., to see whether the building will stable or not. Similarly, in blasting also nowadays numerical simulation is being carried out, some softwares are available. So, here the designed blast can be simulated and to see the results of that same. Prior to the implementation, this simulation may be carried out on the desktop computer, and based on those results that can be modified, remodified, and when the result will be satisfactory, then only it will be implemented, and then the practically what is the results obtained, that will be compared with the numerically simulated results. So, this similar process are available. There are many softwares available. One software Dr. Behera will demonstrate you, give you the idea of that. So, prior to that, let us retrospect the previous lectures. So far we have covered the basic drilling and blasting technologies. We have also understood the explosives and explosive rock interactions, and we have understand how the blast designs are carried out for the surface and underground blastings, and how to evaluate the results maybe in terms of fragmentation, fly rock, ground vibrations etc. We also understand the how to calculate the financial implications of the drilling and blasting, what could be the possible drilling cost, what could be the blasting cost, how that can be calculated, how the blasting results can be defined in terms of powder factor etc., are already discussed. We have already gone through the rock and rock mass properties and their influence on the blasting results. Some of the special blasting techniques like ring hole blasting, long hole blasting, underwater blasting, these are already discussed. So, in this lecture our objectives are basically to understand how the engineering problems are analyzed, basically the numerical simulation techniques, numerical methods of solving the complex engineering problems. Those are will be discussed in this lecture, and one examples of physical blast experimentation, how that is simulated in the ANSYS explicit dynamic model, that will be discussed here. There are many other softwares also available, but as this software is available with us here, this lecture is made based on that. So, now I request Dr. Behera to carry on the next part.
Thank you, sir. Now, let us discuss how we have analyzed the engineering problems which we are facing in day-to-day life. So, there are two types by which we can analyze our engineering problems. The first one is the physical experiment, and the second one is the mathematical model. In the physical experiment, we conduct physical experiment on the field in the actual scale, or in some cases in the reduced scale in the laboratory scale. But the problem is that it is time consuming and costly, and the limitations is there is a problem for extrapolation. Suppose we have conducted some experiment in the laboratory scale and we want to know the result in the actual field scenario, then the extrapolation there is some limitation, and However, the results which we will get in the physical experiment, that is the real result. And in the mathematical model, the first one is the analytical solution. In the analytical solution, what we will do, we have assumed some simple geometry and we have applied some mathematical formula, like the simple formula, like force formula, F equal to ma. So that kind of mathematical formula can be applied for solving some basic mathematical models. However, those analytical solution can be applied only to simple geometry. So in the real life scenario, we are facing different type of complex geometry, and such type of complex geometry can be analyzed through the numerical solution. Now let's see, as I have already told you, the analytical methods like the direct integration, Laplace transform, those methods can be applied to simple geometry like the circles, like the sphere type of geometry. But now the question is, in the real life we do not have such type of simple geometry. So like this is the jet engine. So to calculate different forces which are applied on this on the different parts of this jet engine, it's not possible to do that calculation through the analytical method. And so how to solve that type of situation? So the answer is the numerical method. And one of the numerical method is the finite element analysis, in which what we do, we approximate the solution by taking what are the boundary conditions and what are the physical parameters are there. We'll take that parameters and we'll solve that problem. And this FEM, the finite element analysis method, that is basically developed for the solid mechanics, but nowadays this method is applied in various types of multiphysics problems. Now let's see the areas where we can apply such type of problems. The first one is the structural analysis, like the bridge problem, like the solid mechanics, like a gear or automotive power transfer problem, like the dynamics where it is dependent on time, like the vibrating structure or the bullet impact, like the thermal analysis, like the heat transfer, and the CFD analysis, like the fluid flow, and in electrical analysis. In such type of cases, nowadays we are using this finite element analysis numerical technique for solving different types of complex engineering problems. Now, ANSYS, a finite element analysis by ANSYS. So as Sir has already told you, ANSYS is one of the commercially available software in which we can do the finite element analysis. So there is one section of ANSYS that is called the explicit dynamic section, and that section is particularly used for blast simulation. So what is ANSYS explicit dynamics? Explicit dynamics is a time integration method used to perform dynamic simulations when speed is important. That means in a very few fraction of second we want to know what is changing. Explicit dynamics accounts for quickly changing conditions or discontinuous events such as free fall, high speed impacts, applied loads, but the time period is very less. Another one, so now let's see where and what type of physical experiments we can analyze, we can simulate through this ANSYS explicit dynamic model, like the drop test, impact and penetration test, breakage, shock wave, and the large deformations due to blasting. There is one section called implicit dynamics, where the dynamic is happening but the time interval is very large, and the explicit dynamic, the time interval is very short. Now let's see the basic procedure of FEA, the finite element analysis. There is one physical model. So we have some situation like the physical situation, and we have to describe that physical model through the ANSYS. Then we'll convert in the FEA model. The basic procedure is we are dividing that model into finite number of elements by meshing that thing. Then we will apply some material properties and the boundary conditions, that means the input parameters like the fixed conditions, like the various external applying force, that type of things, that is called the boundary conditions. Then the FEA theory will choose the approximate function and formulate some linear equation and solve them. That is the core of the FEA. And now we will visualize the result and explain the result. This is the 4 procedure which we will do in ANSYS explicit dynamic analysis. Now let's see the basic introduction to ANSYS workbench, the command menu, user interface, and different features of ANSYS. So you can go to the start menu and click on the workbench to open your ANSYS window. It will take some time. It will load all the necessary features and it will verify the license. Then the project window will open like this. This is the ANSYS workbench interface. In that interface, this is the part where the menu sections are there, like the file, view, tools, and different menu bar sections. Next, this part is called the project schematic, where different workflow will do, and this one is the toolbar section. There are different toolbars which you can read it: analysis system, component system, custom systems, and design explorations. Now we'll do, you can see here there are different types of analysis systems are available. Like I have already told you, we can do the CFD analysis, electrical analysis, static mechanical analysis. What we will do, we will do the explicit dynamic analysis. Like we are doing the blasting simulations, and here time is important, so we will do the explicit dynamic analysis. So how to open that thing, that section, to the project view? So you can drag that thing to the project view, or you can double click that thing and the section will appear here. So now the thing is that you can rename that section for your better interaction with that section. And now you can see here the project is on not saved. You can go and save that project in a particular folder, so that all your required files or related files can be saved in that particular folder. You can give a particular name to that folder, so that all the associated files can be saved in that particular folder. And the benefit is that you can open that folder later on also. So like this, your project has been saved in a particular folder, and you can open that thing, that particular folder again. Now let's see. Now let's this is the particular section that is called the explicit dynamic section. I have zoomed that part, and each part of this section is called a particular cell. We have already named that section, that is blast simulation. Okay, so this is called the system, the ANSYS explicit dynamic system, and there are each cell, will work on each cell to carry out our simulation part. The first one is the engineering data, that is used to define the material to be used for the analysis. Let us suppose we are doing the blasting analysis in a particular rock mass, and that rock mass is sandstone, that may be coal, that may be iron ore. So we have to define that rock mass material properties. Suppose it is sandstone, then we have to provide the sandstone material properties, and we are doing blasting by using, let us suppose, ANFO explosive or TNT explosive. Then we have to define that explosive in that engineering data properties. Then the geometry section, you can add and create geometry for analysis. Suppose you are doing some stress analysis for a particular bridge, then you have to design that bridge, how that bridge has been designed. So you have to design that thing. So that is called the geometry section. And in the geometry section, you can add something. If you have some design that is designed in the CAD software or SolidWorks, you can import that geometry. Also, you can create a geometry in ANSYS explicit dynamic model also. The third one is the model that is used for the mechanical analysis system and used to discrete the geometry into finite element in the model part. In the setup part, you have to provide the boundary conditions. Boundary conditions like if you have any fixed boundary, if you have any infinity boundary, if there is any gravitational force, if there is any external force acting on that thing, anything that will be your boundary conditions. Next one is the to solve the analysis problem based on the conditions defined. In the solution part, you will solve the problem, and the result part, it is used to display the result as per your user specified format. So different types of format you can analyze, you can visualize your results. This is the 7 steps, 7 cells of this system. Now let us see what is our problem. So there are different types of problems. As I have told you, we can simulate that thing. Our problem is the how to simulate the blasting thing. In day-to-day life, the rock blasting has many challenges like fly rock, airborne pressure, backbreak, formation of boulders. There are various types of negative impacts are associated with the blasting. So what we do, we want to get some optimal breakage limit. So we want to reduce these types of negative impact, and we have to improve the productivity. So what we have to do, as we have already discussed, there are two things by which engineering problems can be analyzed. First one is the physical. So we can do the physical practical field experiments. Suppose we will take 100 kilo of explosive and we'll do the blasting, we'll check the result. Again, we'll do the 150 kilo of explosive, we'll check the result, and so on. We can do the physical experiments and we can check our result, whether we are getting the optimum result or not, maximum productivity and less negative impacts. So like by varying the designing properties, blast design, the input parameters like the design properties, charge properties, rock mass properties, different input parameters by varying, we can do our physical experiment. But conducting the physical experiment is time consuming and also expensive, and in some situation it is not possible to do the physical experiment. Suppose we want to check whether that bullet can penetrate somebody's head or not. So such type of experiment we cannot do that thing directly. So before doing such kind of experiment, we should simulate that thing, whether up to what extent our results, what type of results we are getting or not. So for that thing, this numerical analysis systems importance has been come. We will discuss one blast experiment which was physically conducted on the field. Like this is the blast design details. We have conducted one blast, like this is the crater blast, and there is one hole. This is one hole of length, of depth 1 meter, and in that hole we have taken the charge around 700 gram of charge we have taken, and the charge length is 665 mm, and this is the design. This is the field picture, and this is the model. So this is the field experiment which you can conduct to check the result. You can see, suppose I want to change the input parameters, like I have to change the charge quantity. Then what I have to do, I have to do the experiment once more to check the result. So this is time consuming as well as very expensive. So here the advantage of FEA, finite element analysis, comes. We can simulate the things by changing various parameters and we can check our result. So now let's simulate this particular experiment which we have done in the field in the ANSYS explicit dynamic model. Like I have told you, there was one hole of length 1 meter. So this block has been designed to represent the rock mass. In that block, one cylinder has been designed to represent the blast hole, and inside that cylinder you can see one green line that is representing the explosive charge column. So the first one, like I have told you, the geometry section, you have to define, you have to represent the physical geometry into the 3D geometry part to do the analysis. The first one is the geometry. Now let's see how to create that geometry in ANSYS workbench. In that geometry section, you can right click and import that geometry to that section, or you can go and design that geometry in that section. Yes, one more thing, here also you can do the geometry part, otherwise you can create one separate system for better workflow of the geometry, better workflow in the ANSYS system. There was this is you can get the geometry and engineering data separately in that system. You can drag that system and you can define the geometry there. So this is the geometry section of the ANSYS design module. Here you can make the design by sketching. There are different sketch functions are available. You can drag and you can create your geometry like this. Like I have already designed that geometry here. You can check. This is the block. The block is representing the rock mass, and the cylinder. There are two cylinders. Likewise, you can design the particular geometry in the ANSYS module. One block, second one is the stemming, and third one is the explosive. Now, the next part is the engineering data. Engineering data for metal properties, like we have taken the sandstone metal properties, and for the explosive it is TNT, and for that stemming we have taken the sand metal properties. In ANSYS has its own material properties. You can easily use that properties for your analysis. Further, if you want to add something new metal properties in your system, you can do that also. Now comes, it is the ANSYS engineering data library. Here we are doing the explicit dynamic analysis. Go to the explicit materials properties. There are lots of explicit metal properties are available there, and for our analysis we will take the TNT, trinitrotoluene, and the metal properties are displayed here. And the second one will take for the stemming, we will take the sand metal properties here, and for sandstone, that metal properties is not available in the ANSYS library, and that we can create here. You can take concrete also for your analysis, but for creating a new metal property you have to click here and you can create your new metal properties. Like I've given some name, and you have to save that file in a particular folder. Then from here you can give different metal properties as per your requirement. I have already taken all the metal properties in the mine sandstone, and here I have taken all the metal properties for the analysis. Now this is one section that is called the explicit dynamic section, and A is the geometry section and C is the engineering data section. You can easily drag that thing and connect that system to the explicit dynamic system. Now in the explicit dynamic section, the engineering data as well as the geometries are loaded. Now the model section. Now I will assign the metal properties to the geometry. We have taken that metal properties, but now we will assign each metal properties to the each geometry parts in that model section. Now let's see. We'll right click and open that model part, and it will open the mechanical simulation section of the ANSYS workbench. It will take some time for loading. Yes, our design has been successfully inputted in the mechanical section. Now you can see in the geometry part, like there are three parts. One is for that block, where we will apply that rock mass property. Second one is the stemming, and third one is the explosive. So yes, for the block we will go here, assign the metal properties. We can assign TNT, sand and concrete. Our sandstone properties has not updated in that system, so we have to go back again to the engineering library section for providing that properties. Let's see. Again you have to open your engineering data section, and here you have to add that properties. After adding that properties, see this symbol is showing, that means that thing is not updated. You have to update that system, so that whatever engineering data we have added, that will come to this mechanical section. Now you can check here, the sandstone is showing here. You can add that thing to that block. Okay, now sandstone has been added for that block, and sand properties has been added for the stemming, and TNT metal properties has been added for that explosive. Likewise, you can assign different metal properties to the different parts of your geometry. Now in the model section, the next one is the meshing. In the ANSYS finite element analysis, you have to discretize your model into finite number of elements. So you have to create the meshing. And for the explicit dynamic analysis, what you have to do, your mesh physics preference as explicit, and you have to generate your mesh, and it will create the mesh like this. And the next one is very important part, that is called the boundary conditions. Boundary conditions means what are the conditions, like we have conducted that experiments in a rock mass where only the top one is the free phase and the rest other are the infinity phases are there. But in our geometry, all 6 phases are like the free phases. Like we have taken the geometry, we have constructed this geometry by 2 meter by 2 meter by 2 meter, and we have defined one hole of actual geometry. So all the phases are behaving like free phases. So what we have to do, we have to define all the 5 phases as the infinity boundary conditions except the top one, so that all the 5 phases will behave like the infinity boundary, and the top one will behave like the free phase situation. So now we'll assign some boundary conditions. In the analysis section, go insert, and there are different types of boundary conditions are there, like the pressure, hydrostatic pressure, force. So here we'll add the impedance boundary conditions, and we'll apply that impedance boundary condition to all the 5 phases except the top one. And for adding that thing, we have to select this phase 1. Here one phase option is there. Likewise, select that phase option, and you can add the infinity boundary condition to all your 5 phases. This is one of the boundary conditions which we are adding right now. Okay, now all the 5 phases, the impedance boundary condition has been added. Now the second boundary condition we will add, that is what we'll add, we will add the standard gravity. So we'll add the gravity in the negative z direction. So z direction, our top of the free phase is there. So in the negative z direction, we'll apply the gravitational force. And the third one will define the detonation point. So where we'll add our detonation point, we'll add the bottom detonation. So we have to hide our block, then we have to hide our stemming part, and below the charge column, we'll add our detonation point like this. We'll add the bottom detonation, and now our detonation point has been added. So three boundary conditions we have added. The first one is the impedance boundary condition to represent the infinity boundary. Second one is the standard gravitational force to represent the normal scenario, and the third one is the detonation point. So likewise, we have added all the three boundary conditions to our model. So what we have to do, first thing we have done, we have created our geometry, then we have assigned different metal properties to our geometry, then we have added the boundary conditions to represent this simulation similar to what the blast we have conducted on the field. Now the next one is the setup. So what we'll do some analysis setting, like we're doing the blast experiment. So our time frame, we'll do some time frame for that thing. In the analysis setting, we can do our time frame and other things like you want to erode the metals or not, different types of setup you can do it. The main thing is you have to set up your end time of this simulation, and that you have to take very few times because it is one explicit dynamic analysis. It's not implicit, so your time frame will be very short. The next thing is the solution. In the solution part, what type of solution you want to check, like you want to check the total stress, total strain, total deformation in a particular line, the different types of solution, what solution you want to check, you can define that thing in the solution section. This is a solution section. Here you can add the like the deformation, strain, stress, different types of solution setting you can. Okay, I have added 2 times the deformation, so I am deleting one thing. So I want to check the total deformation, what is happening after the blasting. Now I want to check the deformation in a particular direction. Particular direction means I want to check what is the deformation on the top surface, like from the bottom, from the top of the hole to one direction. Suppose I want to check the distance of, like let us suppose the backbreak distance, the hole will blast and what amount of crack will generate on the surface I want to check. For that I will take one directional deformation. So for adding the directional deformation, you have to assign that particular direction where you want to check your deformation. So you have to add one path, particular path. On that line I want to check that deformation. So here you can add your points, like you have to add this point, and from this point you can check the deformation on that particular line to the end of that cube. So I'm adding the point. This block is 2 by 2 by 2 and that charge hole diameter is 160 mm. So accordingly I'm adding my points. So the middle point will be 1.08 and the last point will be 2. Accordingly I'm adding that values. So likewise you can check on that particular line. Also I want to check my total deformation. Then on the deformation tab you can add that line, on which line you want to check the deformation. So all the metal properties has been added that I am checking. Okay, now what you have to do in the solution tab, you have to solve your solution. You have to start your solution. Okay, it will take some time for starting the solution. Okay, now the ANSYS Workbench solution status is showing here, and you can check the status from here. It will take around 3.7 hours. It will take more times also if you do more, if you do more fine meshing, then it will take more time for the processing. Okay, now let's check the result. Now let's see the solution. Yes, this is the yes. When this is the three things. First one is the engineering properties, and another section is the geometry, and the third section is the explicit dynamic. And here are the each cell of that explicit dynamics, like engineering data, geometry, model, setup, solution, results. Now we can check all the 7 sections has been marked with the tick mark. That means all the sections has been completed properly. So now you can check the result. Yes, I've added the result. So this is the isometric view, and I have cut that isometric view in that one section, and this is our deformation, and this is the top view of the deformation, and this is the directional on that particular line. The amount of deformation is showing here. You can see that thing in the ANSYS window also. Let us suppose after the solution you will get the result like this, and this is the isometric view. You can use this section tab to have this sectional view, and likewise you can check the sectional view of the result, and you can check the simulation in a particular video format how the deformation is happening, and all the results, all the tabulated data you can obtain from here.
There are some drawbacks in this process. One is that it is very difficult than in natural cases when we are doing it for the rock blasting etc. We are having the discontinuity planes, we are having voids etc. Those are may not be known to us, may not be may be unknown to us. So, those things, incorporate those things in the model is very difficult. It is not impossible, but it is difficult. And see, in this particular case we have considered a 2 meter by 2 meter rock mass, or you can say 2 by 2 by 2 meter rock mass, and we have placed 1 meter hole there. So, it is something like that where a particular cube of rock mass is kept, but in natural case it is not like that. Earth is an you can say infinity ground you can consider. So, that considerations if you are carrying out in a numerical modeling, it will take days, and not only days, it will take months to solve that one, because the meshing will be too much. So, the number of calculations will be very more and very large, and that is very difficult to solve for the computer system. So, depending on the size of the block, the analysis time is depending. So, for real life cases where long hole blasting, ring hole blasting, those big things are there, that high capacity computers are also very difficult to solve. It is difficult for those computers to solve that in a real time, or you can say in a given time frame. So, that is why these are the difficulties, and this leads the practical results are far away from the simulated results. So, often it is found that it may not match very properly. So, those things are difficulties, especially where the blasting is carried out continuously in a bench. The breaks occurred due to the previous blast in that bench where the fresh blasting is being carried out cannot be modeled, because there is no existing model is available where the cracks will be visualized or cracks will be estimated and that can be incorporated there. In those cases, this is another problem, we cannot use this numerical modeling techniques. But anyway, where the fresh designing is being carried out, in those cases that use of this numerical analysis may be little bit helpful for the blasting engineers to understand or to have a prior idea about the possible result in that particular blasting. So, as these things are the modern techniques has come out, maybe in coming days future the better modeling techniques will be possible with this. So, that will be a benefit for the mining engineers or blasting engineers to use. In this case, there are few things I would like to give you, that one is that numerical modeling technique, here the properties has to be given, all those material properties has to be given properly, but in practical cases that may differ from that understood property. Second is that there are different models available. Suppose from explosive to energy conversion, you may have a Hugenoid model, you may have JWL model, you may have Wood-Kirkwood model. So, those models, choice of those models are very important. Similarly, where you are calculating the failure criteria, that choice of those failure criteria is very important, how that failure criteria has to be considered. Based on that, it will show the distance of the damage, fragmentation, etc. So, the choice of the models, choice of the criteria and the material properties are also very important, that has to be kept in mind. So, we give this is, you must consider this is a one just introductory lecture about the numerical analysis for the blasting problems. In maybe in future it is possible that one course may be given on this, so that it will be benefited for you to carry on practically practice this numerical modeling in blasting. So, this is only this much for this numerical analysis part. Thank you.